Welcome back. Hey, let's finish up our conversation in thermodynamics by talking about our last topic, which is called the Gibbs free energy. So what does it mean by it being free energy? Well, don't really worry about it. Just understand that what we're looking at here is a symbol that we denote as delta G. So what free energy is not really that big of a deal. Understand that what we're measuring with delta G is what we call spontaneity. So in other words, it's how spontaneous a reaction is. If you're thinking to yourself, well, what does that mean, spontaneous? It means, does the reaction occur on its own? And this is something that we can determine by looking at the values of delta H and delta S. Now we have two different ways that we can determine delta G, or in other words, spontaneity. We have one equation, which looks like this. Delta G, and technically these are all standard states, equals delta H minus T delta S. So if we know delta H and delta S, for whatever reason, whether it's given to us or it's something that we found previously, we can use the relationship between H and S to figure out delta G. But notice that we have one more thing that seems to contribute to whether or not something is spontaneous. That is temperature, which we measure in Kelvin. So temperature directly affects whether or not something is spontaneous or not. And again, spontaneous just means that the reaction occurs on its own. If I have to heat it up, or if I have to mix it, or if I have to do anything to make the reaction start, that would not be considered spontaneous. A spontaneous reaction is something that happens without any help. Okay, so let's look at the units in this particular equation, because this is the tricky part. I kind of mentioned this in the previous video, but I want to make sure that I clarify this again. Delta G in this equation is measured in kilojoules per mole. And it's also given in kilojoules per mole in the book. Delta H is also in kilojoules per mole. However, delta S is given in joules per mole Kelvin. Notice that that's in joules. So that means that even if we calculate delta S, whether it's through the book or any other means, that number is always going to be given in joules. Before we can plug delta S into the equation, we have to make sure that delta S is in kilojoules. So make sure that you keep that in mind. Don't just plug delta S straight into the equation before converting it into kilojoules. All right, let's keep going. So let's look at a problem that we've kind of been playing with a lot. We've done this particular reaction for both delta H and for delta S. And now let's use the values to see if we can calculate delta G. So take a second. Flip back into your notes, find the delta H value for the combustion of methane, and find the delta S value for the combustion of methane, and see if you can figure it out, figure out delta G, we'll say at 298 Kelvin. Most of the problems that we do in this class are going to be at 298 Kelvin. Maybe we might not be at 298 Kelvin, but, you know, most of the time, if not stated, you could just assume that that's the temperature that we're at. So go ahead and see if you can calculate delta G using the above equation and the numbers that you found before. Come on back when you're... Okay, so all I did was pull the numbers straight from the previous problems I did in the notes. The delta H for the combustion of methane is negative 803. The delta S was 5.15. So I had to move the decimal over because this is in kilojoules, not in joules. And then I just multiply that by the temperature, which again is 298. Bing, bang, boom, I get negative 801. Now, whether or not that negative sign has an importance, that's something that we're going to talk about in just a second. It does, but we're going to talk about the meaning of the sign in front of delta G in just a second. But first, let's also talk about the second way that we can calculate delta G. So just like with the other two, we can calculate delta G of a reaction by taking the sum of the G values for the products and subtracting them from the sum of the G values from the reactants. And you might have kind of guessed this was going to happen, because if you look in the book, you have three columns. We've used the H column, we've used the S column. The G column is used for the same thing. We just look up the values and we just plug it in and we take care of it. So let's look at this problem here on page 702, number 14. It says compute the Gibbs free energy, which just means delta G, for the following equation. Let me go ahead and write the equation down and then we can get started. All right, so I'm all good. So now that I have these all here, we are going to look into the back of the book and we are going to just try and find the delta G values for these. We plug them into the equation just like we always have, and we solve for delta G. I'm going to give you a chance to try this out on your own. Come on back when you finish. Okay, so hopefully this is what you got. Again, all I did was plug in values from the table. I'm not making these numbers up. They're just from the table in the back. Negative 1362, that's for BaSO4. Negative 131.228, that's for HCl. I multiply it by 2 because there are 2 moles of it. If I take the sum of both of those things, I wrote that below it. That's negative 1,624.7. I do the same thing to the reactant side. That's negative 1,567.74. My overall answer is negative 57.0 kilojoules per mole. So again, negative. So what do the signs mean for delta G? We know what the signs mean for H and S, right? So for H, a positive means endothermic, a negative means exothermic. For S, a positive means increasing disorder, but a negative means decreasing disorder. But what does it mean for G? All right, so for G, if a reaction is considered spontaneous, again, meaning that it happens on its own, it is considered, it is negative. So a negative delta G is a spontaneous reaction. This term here that we have in the notes, this one, exergonic, that's not really a term that we use very much anymore. The term that you'll probably see, whether it's in this class or in the future, I gotta remember how to spell thermodynamic, is thermodynamically favored. That's kind of the more appropriate term, so just keep that in mind. Reactions that are non-spontaneous are going to be positive, which means they are not thermodynamically favored. And then if I have a delta G that is 0, then that means that I'm both spontaneous and non-spontaneous. Or in other words, I'm spontaneous in both the forward and reverse direction, which implies that I'm at equilibrium. It's not something that we're going to see very often in this class though, but just keep in mind what the value means. Mostly, keep in mind the first two. If delta G is negative, that means it's spontaneous. It means it occurs on its own. If it is non-spontaneous, it's going to be positive. Okay, so we can actually put together a little table for this, and it kind of helps us visualize. I know the table in your notes is a little different, so if you could make a little of an adjustment, add a delta G column to this table, it'll really help you out. Now, while we're talking about this table, I want you to consider the equation delta G equals delta H minus T delta S. And I'm going to be kind of playing around with this equation as we are working, so just keep that in mind. I'm going to kind of put parentheses around these because I'm going to be erasing and adding numbers to this equation. And you don't have to do that with me. It's going to be easier for me because I can erase and write back. But I'm going to kind of use that as an explanation as to why the table works the way that it does. So let's consider how H and S affect delta G. Let's look at it. So let's start with the things that the universe likes the most. We've learned in the past that the universe prefers exothermic reactions, right? We like energy being released. And the universe also prefers to trend towards disorder, which means that we have a positive S. So what is delta G going to look like in this situation? Let's say that we have a negative 50 here and a positive 50 here. What is the value of this number always going to be? Well, negative minus a positive number, it's always going to be a negative value, right? So it doesn't matter if this is a larger number. It doesn't matter if this is a smaller number. We're always going to get the same delta G value, and that delta G value is always going to be negative. So, in other words, if we have an exothermic reaction that trends towards disorder, we are always going to be spontaneous. So this is always spontaneous. Spontaneous. So that means that no matter what, we are always spontaneous. Now let's think about it the other way. Let's think that if I have an endothermic reaction, which is not favored by the universe, and a reaction that trends towards or away from disorder, then that means, again, not favored by the universe. If we were to think about it that way with our equation, where we have a positive 50 here and a negative 100 here, it doesn't matter what this number is going to be, because a negative and a negative is always going to be a positive. Delta G is always going to be a positive number, which means that this is always going to be non-spontaneous, or in other words, it's never spontaneous. So what this helps us do, the reason why this table is useful is that even without doing any sort of calculations, as long as we know what the sign is for H and S, we can make an assumption about what the sign should be for G. So let's get a little trickier. Now what happens if we have a exothermically favored reaction, a thermodynamically appropriate reaction, right? Like the universe likes this because it's exothermic. But it is a entropy unfavored reaction, meaning that it is going to be a negative. We are trending away from disorder. What's going to happen to G? Well, let's kind of think about it. We can play about with the numbers a little bit. If I have a negative 50 and a negative 50, then what's going to happen to the G? Well, let's get a little bit more extreme, I guess. Let's say that it's like negative 100. In this situation, the S is going to be large enough that the going to be negative. But wouldn't you agree also that if this number was smaller, then it would then be positive? So it seems like it depends on the value of the S, but what also determines the value of the S? The T. The T has a factor, or in other words, the temperature has a control over this spontaneity. So in other words, honestly, we don't know. That's supposed to be a question mark, but my question marks are bad. That's better. Honestly, we don't know. So because we don't know, and because this is dependent on temperature, we have to say that. We say that this is sometimes spontaneous. I'm going to abbreviate spontaneous like this. And it's sometimes spontaneous at low temperatures. If you're kind of thinking like, well, that doesn't make any sense, let's consider ice. Think about ice. Think about water freezing. Does water freeze spontaneously? If you put water on the counter, does it just freeze? No. But wouldn't you agree that water does freeze by itself if you put it in the freezer? Yes. So it seems like the process of water turning into ice is something that only occurs by itself at low temperatures. That's what this means. So in other words, some processes have to happen at low temperatures and then they occur spontaneously. You could probably assume that there's one more thing that we can look at. If H is positive and S is positive, we're going to have a very similar situation where we're going to be dependent on T. So we are not going to know what delta G is, but we can say that we're going to be sometimes spontaneous at high temperatures. And for this, I'd ask you to consider ice again. So now we're going to take our ice out of the freezer and we're going to think about it. So does ice melt into water spontaneously? Think about it for a second. If you answered yes, yes, of course it does, then I would say, well, does your ice just melt in the freezer? No, I guess it doesn't. But if you said no, it's not spontaneous, then I would say, well, doesn't your ice melt on the counter? Like if you just put a piece of ice on the counter, doesn't that melt? Then you'd say, yeah, okay, yeah, it does. So again, the ice spontaneously goes from a solid to a liquid at high temperatures, which means that that reaction or that process is dependent on temperature. It is only spontaneous at high temperatures. So again, this is why temperature is another factor that affects whether or not something is spontaneous. And you can find this very table in your book. It's a very similar table on page 699 in your book. But this is the idea. So again, for delta G, we're mostly just looking at whether or not something is spontaneous. If we are always going to be universally favored, meaning negative and positive, then that's always spontaneous. And you just kind of follow this table as best you can when you are working through stuff. Okay, let's look at a little practice. We're not going to do all of these, but if you flip into your book, there's a couple of good problems here just to kind of make sure that you're good with it. I think I just want to do like 15 and 16. I don't really want to do 17. I don't think it's that great of a problem. So let's look at this one. It says compute, or in other words, calculate delta S for the following reaction. It gives you the reaction. So this is a review from yesterday, really. We're going to go into the back of the book and we're going to try and find the delta S values for those different values and give it a try. I'll put up the answer, but you try and do it yourself and then come on back when you're finished to check your work. What you should have found is that you should have found your delta S to be 32.9 kilojoules, or excuse me, joules per mole Kelvin. Now, if you didn't get that, make sure you make note and maybe we can talk about it in class. Let's try another one, 16. 16, this time we are determining the delta G. So we are not given H and we're not given S. So we're going to have to do delta G with the table. We can't use the H and S values unless they're given to us, or unless we calculated them previously. But that seems like too much work. Let's just use the G values from the table. So go ahead and give this one another pause. I'll put up the answer when you're finished, and you'll check it, and then we'll move on from there. Okay, so I got positive 546 when I did this. And the next part of the problem, it asks you to state whether or not this is spontaneous or non-spontaneous. So remember, delta G, if it's positive, it means it's not spontaneous. And that's all it'll take. So again, I don't want to do 17. I think it's not very good of a problem. It's really not that good of practice. If you want to do it, you can, but I don't really think it's that worth it. That's it. That's delta G, and that's thermodynamics. We'll see you in the next one.